Okay, let's dive straight into this explainer and build a solid mental model of exactly how we track spacecraft in three-dimensional space using Keplerian elements. You know, if you've ever looked up at the night sky and spotted a satellite steadily tracking across the stars, you might have wondered, how do scientists and engineers know exactly where that thing is, where it's headed, and how fast it's going? Without this exact mathematical framework, literally everything from the International Space Station to the GPS chip right there in your phone would be completely lost in the void. Now, the math governing the cosmos can seem, well, incredibly daunting, but the absolute beauty of orbital mechanics is that it can be distilled down into a really elegant, highly structured framework. So today we're going back to the foundational principles to understand exactly how that framework actually operates. To keep from getting overwhelmed, we're going to build an orbit from scratch, piece by piece. Here is our roadmap. Navigating in 3D space, orbit size and shape, tilting the orbital plane, pinpointing the satellite, a real-world example, and finally, time and special cases.
All right, part 1, navigating in 3D space.
Think about it this way. When a car drives down a highway, finding its position is relatively easy, right? Because it's essentially just moving along a one-dimensional line on a 2D map. But a satellite, it moves in a vast, three-dimensional void. To fully describe its precise movement and location in that space, we need exactly 6 independent parameters. Not 5, not 7, exactly 6. And you can remember them with this brilliantly simple 6-step mnemonic: size, shape, tilt, turn, periapsis, and position. They essentially group into 4 logical buckets. First is size, second is shape, third is plane orientation, that's your tilt and turn, and finally, position and direction within the plane, covering periapsis and position. If you just lock in size, shape, tilt, turn, periapsis, position, you've got the exact sequence you need to master the whole shebang.
Moving right along to part 2, orbit size and shape. Let's define our 2D track. So before we even worry about three-dimensional space, we need to draw the actual track our satellite is going to run on. And every single orbit starts with one simple question about its overall scale. How large is the orbit? Are we just skimming the top of the atmosphere, or are we soaring hundreds of thousands of kilometers out toward the moon?
We answer that question with our very first element, the semi-major axis. It's represented by the lowercase letter a. Think of an elliptical orbit kind of like a slightly squashed circle. The longest diameter across that ellipse is your major axis. Cut that straight in half, and you have the semi-major axis. It strictly dictates size. A larger value generally means a larger orbit, a longer orbital period, and, interestingly enough, a lower average speed for the spacecraft. It's the fundamental anchor for how long it takes a satellite to complete one full revolution around the Earth.
Now, what's really fascinating here is how the eccentricity value completely reshapes our orbit. Eccentricity, represented by the letter E, defines our shape. If your eccentricity is exactly 0, you've got a perfectly circular orbit. As that number grows between 0 and 1, the orbit stretches out into an ellipse. So a low Earth orbit might have a tiny eccentricity of, say, 0.001, making it virtually circular. But a highly stretched orbit might sit around 0.7. And if eccentricity hits 1 or greater, the spacecraft is on a parabolic or hyperbolic escape trajectory, meaning it's literally breaking free from Earth's gravity entirely and never coming back.
All right, part 3, tilting the orbital plane. Let's lift this thing into 3D space.
Imagine taking that flat ellipse we just drew and laying it flat on a table, where the table represents Earth's equator. Now we have to ask, how tilted is this orbital plane? We absolutely need to know this exact angle to figure out what parts of the globe the satellite is actually going to fly over. Inclination is what measures this tilt relative to Earth's equatorial plane, ranging from 0 to 180 degrees. At exactly 0 degrees, the satellite just circles directly over the equator, moving in the exact same direction the Earth spins. But if we tilt it up to a 90-degree inclination, that gives us a polar orbit. The satellite flies straight over the North and South poles. This is fantastic because as the Earth rotates underneath it, a polar satellite will eventually see the entire globe. Now, an angle over 90 degrees means the satellite orbits retrograde, which means it's traveling backward, opposite to Earth's normal rotation. Otherwise, it's prograde. Basically, a higher inclination allows the satellite to pass over much higher northern and southern latitudes.
But wait, we aren't quite done orienting our plane yet. We know the tilt angle, for sure, but we also need to lock down exactly which way that plane is facing out there in the solar system. Imagine a tilted hula hoop around the Earth.
You could easily spin that hula hoop all the way around the planet without ever changing the actual tilt angle, right?
So, to lock it firmly in place, we use the right ascension of the ascending node. Thankfully, we just call it RAAN, or the Greek letter omega. RAN acts as our anchor in space. It tells us the precise direction the plane is tilted when the satellite crosses the equator from south to north. That specific crossing point is called the ascending node. We measure the angle eastward from a fixed reference direction in space, specifically the vernal equinox, which is a fixed point aligning with the sun on the first day of spring. So, to recap, inclination tells us how much it's tilted, RAN tells us exactly which direction it faces.
Okay, part 4, pinpointing the satellite. Time to locate the spacecraft.
Our 3D plane is perfectly positioned in space. Now, we just need to orient our ellipse inside that plane. Enter our fifth element, the argument of periapsis, or lowercase omega. Remember, every elliptical orbit has a closest point to Earth, called the periapsis, or perigee if we're talking about Earth. While RAAN positions the entire plane, the argument of periapsis rotates our specific elliptical shape within that very plane. It's the angle measured from the ascending node along the orbit path right to the periapsis. In plain English, it tells us exactly where the lowest point of the orbit is physically located.
The entire track is completely built. It's scaled, it's tilted, it's rotated perfectly. But we still need to locate our moving target. Where is the actual satellite right now at this exact moment?
We find it using the true anomaly, which is represented by the Greek letter nu. The true anomaly is measured from the periapsis all the way to wherever the satellite currently is. So here is the absolutely crucial point. Unlike the first 5 elements, which are static, true anomaly is completely continuous. It is constantly changing as the satellite sweeps around the planet. At periapsis, the true anomaly is exactly 0 degrees. Halfway around, at the farthest point, the apoapsis, it's 180 degrees. And keep in mind, because gravity pulls harder the closer you get, the satellite actually speeds up near periapsis and slows down near apoapsis. That means this angle doesn't just increase at a nice steady rate.
Let's move to part 5. Let's turn all this theory into applied science by decoding a real set of telemetry.
Imagine you're an aerospace engineer staring at this block of raw data on your monitor. You see A equals 7,000 kilometers, E equals 0.01, I is 98 degrees, big omega is 45 degrees, little omega is 30 degrees, and nu is 120 degrees. I mean, out of context, it looks like complete alphabet soup. But let's actually decipher what it means using the framework we just built. Just by matching our elements, we instantly know a staggering amount about this spacecraft. That semi-major axis of 7,000 kilometers, that tells us the satellite is relatively close to Earth. An eccentricity of 0.01 means it's in a nearly perfect circular orbit. An inclination of 98 degrees tells us it's in a near-polar orbit, traveling backwards, or retrograde, relative to the Earth's spin. Plus, we know its ascending node is 45 degrees east of our fixed space reference, its lowest point is 30 degrees past that node, and the satellite itself is currently 120 degrees past its lowest point. Just 6 numbers, and we literally have total situational awareness. It's a real game changer.
And finally, part 6, time and special cases. Because we have to account for the edge cases in the math and the messy physics of the real universe. Our mathematical model is incredibly robust for sure, but the trouble really starts when our values hit exactly 0. When eccentricity or inclination equals 0, the classical definitions just break down. Think about it. If an orbit is perfectly circular with an eccentricity of 0, there literally is no closest point. Every point is equally close. That makes the argument of periapsis completely undefined. Similarly, if inclination is 0, the orbit never actually crosses the equator from south to north, so the ascending node completely disappears. In these tricky edge cases, engineers actually have to use combined angles, like the argument of latitude or true longitude, just to keep the math working smoothly.
But math isn't our only complication. Physics plays a massive role here. The real universe is incredibly messy, because real orbits are constantly warped by physical forces, things like Earth's non-spherical gravity field, drag from the upper atmosphere, the gravitational pull of the sun and moon, solar radiation pressure, and even intentional spacecraft maneuvers. Our orbit is actually never truly static. Because of this, our 6 classical elements are only perfectly accurate for one very specific moment in time. We call that timestamp the epoch.
So if dynamic forces are constantly shifting a satellite's trajectory, What happens to our spacecraft if we ever lose track of its epoch? Well, I'm going to leave you with that thought to chew on. It highlights exactly why time is the ultimate anchor for literally everything we track in the cosmos. Without knowing the exact epoch, that precise timestamp for our 6 Keplerian elements, our perfectly calculated orbit quickly becomes a ghost of the past, drifting completely away from reality as physical forces bend it out of shape. Understanding these 6 elements and knowing exactly when they apply, well, that is the true mastery of orbital mechanics. Thanks for joining me for this explainer today, and keep looking up.